Hi everyone. In Learning Unit 5, we're going to learn about acid-base titration. At the end of this learning unit, you should be able to illustrate titration of a strong acid with a strong base, describe the difference between an endpoint and an equivalence point in an acid-base titration, identify the equivalence point in an acid-base titration from the pH titration curve, and finally, illustrate titration of a weak acid and a strong base. In the second part of this learning unit, you should be able to distinguish titration curve of polyprotic acid with a strong base and polybasic base with a strong acid. Identify the equivalence point in an acid-base titration from the pH titration curve. Identify suitable indicator for an acid-base titration. Apply titration in Jadal analysis and evaluate acid-base titrimetry. Before we proceed to the three types of titration that we are going to learn in this learning unit, let's take a look at some of the important definitions and terms for acid-base titration. Standard solution. Standard solution is a reagent of a known concentration which is used in the titrimetric analysis. As you have learned in experiment 1 of practical analytical chemistry, you know that standard solution is obtained from the titration or standardization of the solution by a primary standard solution. All right. Titration is a process which is performed by adding a standard solution from a burette or any other liquid dispensing device to a solution of the analyte until the point at which the reaction is believed to be completed. When we talk about titration, we are going to encounter the terms equivalence point. What is equivalence point? Equivalence point occurs in a titration at the point in which the amount of added titrant is chemically equivalent to the amount of analyte in a sample. When we talk about chemically equivalent, it means that it has the same number of mole between the titrant and also the analyte. Now, there is another term which is equally important in titration process. This is back titration. This is another type of titration which is a bit different from normal titration. Back titration is a process in which an excess of the standard titrant is added during the titration, and the amount of the excess is determined by back titration with a second standard titrant. It means that back titration is also often called indirect titration. It is a two-step titration process, and the details to back titration concept is given in another video which is available on eLib. In this instance, the equivalent point corresponds with the amount of initial titrant is chemically equivalent to the amount of analyte plus the amount of back titrant. Another important term which sometimes is confused with equivalence point is the endpoint. What is endpoint? The endpoint is the point in titration when a physical change occurs that is associated with the condition of the chemical equivalence. Equivalence point, on the other hand, occurs in a titration at the point in which the amount of added titrant is chemically equivalent to the amount of analyte in a sample, meaning to say that equivalence points is the theoretical chemical equivalence between the titrant and the analyte during titration, whereas endpoint is the point which is visible physical change occurs to the titrant and also to the analyte. Sorry, not to the titrant, but to the analyte. Okay, during the end of titration process where chemical equivalence is perceived to be reached. Okay. Indicators is another term which is often used in titration process. Indicators are used to give an observable physical change. Just now we talk about endpoint where we have a physical change occur in the analyte. So how do we visualize the physical change? We visualize the physical change during titration by adding indicators to the analyte. Okay, so the indicators are used to give an observable physical change at the endpoint or at near the equivalence point by adding them to the analyte. The difference between the endpoint and the equivalence point should be very small, and this difference is referred to as titration error. So, titration error is equal to the difference between the actual volume used to get to the endpoint and the theoretical value of reagent required to reach the endpoint. Okay, so we have EP, which is the endpoint. Okay, this is the experimental value of endpoint or physical change seen or visualized through indicator during a titration. And VEQ is the equivalence point, which is the theoretical value of reagent when the titration reach the chemical equivalence between the titrant and also the analyte. What is acid-base titration? Acid-base titration is a quick and accurate method for determining acidic or basic substance in many samples. The titrant is typically a strong acid or base, and the sample species can be either a strong or weak acid or base, right? So whenever we talk about analyte, analyte is the substance that we put in the conical flask during titration, and the titrant is normally a solution that we put in a burette or any liquid dispensing device during a titration. Okay, so this one is titrant, and this one will be the analyte. And normally we add indicators in the analyte to visualize endpoint. Okay. There are many types of acid-base titration. For example, we have titration between strong acid and strong base, weak acid and strong acid and weak base, polyprotic acid and strong base, polybasic base, and strong acid. All the calculations for each of the titration type is different, but in this learning unit, we are going to go into details on the calculation for 1, 2, and 3, which is titration between strong acid and strong base, titration between weak acid and strong base, and titration between strong acid and weak base. However, for number 4 and number 5, we are going to look at the curve type when we have a polyprotic acid and strong base titration and a polybasic base and strong acid titration. We're not going to look into details on the calculation problems, but we are going to look at the curve type that we will get for both of the titration type. Okay. Now, let's look at the first type of acid-base titration that we are going to learn in this learning unit, which is the strong acid and strong base titration. In strong acid and strong base titration, there are 3 regions of the titration curve that represents a different kinds of calculation. So whenever you consider a titrant, which is strong base, for example, sodium hydroxide, and an analyte, which is a strong acid, for example, HCl or hydrochloric acid, there are 3 points on the titration curve that we should know how to deal with, which is before the equivalence point, at the equivalence point, and after the equivalence point. I hope you can jot this down because there are different formula for the points before equivalence, at equivalence, and after equivalence. But before that, let's take a look at some theories on strong acid and strong base titration. Whenever we have a strong acid titrated with a strong base, the net reaction is always hydronium ion reacting with hydroxide ion, giving us H2O. Or, in detail, let's say we have a titration between HCl, which is a strong acid, and a strong base, sodium hydroxide. It will yield salt, which is NaCl, and water, which is H2O. This is what we have learned in Learning Unit 4, Acid-Base Equilibria, whereby any reaction between a strong acid and strong base will result in salt and also water. What happens when those reactions give us salt and water? It means that we can perceive or we can predict that the pH at equivalence point is always pH 7. This is because we have a reaction between a strong acid and strong base, which yield a neutral salt and also water. So water, basically the pH is 7. And we know that every time we have a strong acid titrated with a strong base, the equivalence point pH is always 7 or neutral. All right. So what happened before the equivalence point? Before the equivalence point, acid is present in excess. How do we know this? This is because considering the analyte is the acid, which is HCl just now. This is just an example. You can use other acid. Let's say we have the analyte in the conical flask. Before any titration happen, it is solely HCl. Because it is solely HCl, it is acidic in pH. Acidic pH. So before we reach the equivalence point, the equivalence point is always 7. So we know that the initial pH is acidic. That's why we know that before equivalence point, acid is present in excess in the analyte. Okay. Now, pH is determined by concentration of excess hydronium ion. Because we know acid is present in excess, so it should be excess in hydronium ion before the equivalence point. So how do we calculate it? Concentration of hydronium ion equals to millimoles of acid minus millimoles of base divided by the total volume. Total volume here represents the volume of titrant plus the volume of analyte. Okay, just take note of this because after this we will look into an example for you to see this clearer. All right. But we know that before the equivalence point, pH can be calculated from determining the excess of hydronium ion or H plus ion using this formula: millimoles of acid minus millimoles of base divided by the total volume of titrant and analyte. Okay, so from this pH, from the concentration of hydronium ion, you know that pH is equal to negative log concentration of hydronium ion. All right. Some more theory about strong acid and strong base titration. So at equivalence point, moles of acid and moles of base are equal. So you have N for acid equal to N for base. Okay. From here, you have the equation MAVA equals to MBVB. Okay. So just take note of this first. And at equivalence point, we know that the concentration of hydronium ion is equal to the concentration of hydroxide ion, and the pH is always 7. The equivalence point for strong acid and base titration is always pH 7. Okay. What happened post the equivalence point? Just now we know that before equivalence point, we have excess hydronium ion, right? And at equivalence point, we have neutral pH, which is pH 7. So what happened after the equivalence point? It should be pH more than 7, which is basic, which means that we have excess hydroxide ion. Okay, so past the equivalence point, we don't have any more acid remaining. Why? Because all the acid have reacted with the hydroxide ion from the titrant. Remember just now, titrant is anything inside the burette or any liquid dispensing device. And analyte is the acid which is normally put in the conical flask. Okay, so past the equivalence point, all the acid or hydronium ions in the analyte has been reacted with the hydroxide ion in the burette or in the titrant. So we don't have any acid remaining. So what happened when we keep on titrating is that we are diluting our titrant. Okay, diluting our titrant means we have excess hydroxide ion. How do we have excess hydroxide ion? Because we keep on dispensing the titrant from the burette into the conical flask. So more OH negative is going into the conical flask. So more OH negative means excess OH negative. Okay. So how do we calculate concentration of excess hydroxide ion? It is millimole of excess hydroxide ion divided by the total volume. So how do we calculate millimole excess? It is millimoles of base minus millimoles of acid divided by the total volume. Total volume is, just now we know, volume of titrant plus the volume of analyte. Okay. Now let's look at the example so we can have a clearer view or a clearer picture about how acid and base titration curve is constructed. Okay. First of all, I would like to mention to you a titration curve is a curve of pH versus volume of titrant. So this would be the pH and this would be the volume of titrant. Okay, the y-axis would be the pH and the x-axis would be the volume of titrant. So this is why we are going to look for pH of our analyte throughout the titration process for us to construct a titration curve. All right. Let's go back to the example. Construct a titration curve for the titration of 100 ml of 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. So we know that hydrochloric acid is a strong acid, and we know that NaOH is a strong base. So first of all, we need to predict or we need to calculate how much volume of titrant. What is our titrant? The titrant is the sodium hydroxide. Okay, so what is the volume of titrant needed to reach the equivalence point? Equivalence point here means pH 7. So how do we calculate that? We know that at equivalence point, moles of acid is equal to moles of base. Okay, so we already know that Ma, what is concentration of hydrochloric acid? 0.1 molar. What is the volume of hydrochloric acid? We know it is 100 ml. What is the concentration of base? 0.1 molar. So from here, we can calculate the volume of base. Okay, using MAVA equals to MBVB, you can find out what is VB, and here it is 100 ml. Okay, so from this, we know that we need 100 ml of NaOH added to the analyte to reach the equivalence point. Before addition of NaOH, what is the pH? We don't know the pH before addition of NaOH. So before any NaOH coming into the conical flask, it is only the HCl inside. Okay, so how do we calculate the pH of the HCl? Without any addition of NaOH. So pH would be negative log concentration of HCl, okay, which is 0.1, okay, equal to pH 1. So what happened? Sorry. Sorry, where's my slide? Okay. What happened if we add 10 ml of sodium hydroxide? So remember, this is before the equivalence point. When we add 10 ml, it's before the equivalence point because we can only reach the equivalence point at 100 ml of titrant. So what happened when we add 10 ml of NaOH, which is titrant? We have excess of hydronium ion of this much. Okay, so this would be millimole of acid minus millimole of base divided by the total volume. So this is the volume of your titrant. This is the volume of your analyte. Remember what is your analyte just now? It is the HCl. So 100 ml is the volume of your analyte. 0.1 molar is the molarity of your analyte, which is the HCl. 10 mil here is the volume of NaOH added to your analyte, which is only 10 mil. And 0.1 molar here is the concentration of NaOH added to your analyte. And the total volume here is the volume of your analyte, which is 100 mil. How do you know 100 mil? It's from the question. You have 100 mil of analyte in the conical flask plus 10 mil of NaOH added to the conical flask through titration process. So from here, you know that you get the concentration of hydronium ion 0.082 molar. So from here, you can calculate the pH by using pH equal to negative log 0.082 molar. So it's equal 1.09. If you look at the pH here, it's an acidic pH. So your answer should be okay, because we know that before reaching equivalent point, the pH should be acidic. And if you see here, the pH is 1.09, which is slightly increased from the pH of HCl or your analyte before any addition of NaOH. So you know that you're doing it right. Okay. Now, repeat step 3 for every 10 mil of NaOH added to the analyte during titration. So after you repeat that, you have calculation for 20 mil, 30 mil, 40 mil, 50 mil until you reach 90 mil. Now what happened at 100 mil? 100 mil is the equivalence point. 100 mil is the volume of titrate needed for you to reach the equivalence point. So before that, if you plot the titration curve using the data that you get from from this table, you calculate the total volume. This is the total volume. This is concentration of excess hydronium ion, and this is pH calculated from the excess of hydronium ion. So if you take it from this table, so and you get the mil of titrant, so you put it into the titration curve, you plot it, so you have this curve. Okay, so you see here the initial concentration of your analyte is pH1. Sorry, the initial pH is pH1, and then after you add in 10 mil, you have pH 1.09, and it gradually increase until 90 mil. Okay, so this is your titration curve before equivalence point. Remember, any calculation before equivalence point is calculation based on the calculation of excess hydronium ion. Okay. Now, we know that the titration needs 100 ml of NaOH to reach equivalence point. Just now we have done calculation for addition of every 10 ml of NaOH until 90 ml of NaOH is added. So what happened when we add 100 ml of NaOH to the analyte? The equivalence point happen. So at equivalence point, the moles of HCl is equal to the moles of NaOH. So since neither is in excess, neither the HCl or the NaOH is in excess, pH is determined by Kw, which is pH 7. Okay, we know that for all titration between strong acid and strong base, the pH at equivalence point is always 7. Okay. So you don't have to calculate the pH by using excess hydronium ion formula. You just have to put that at equivalence point, the pH is 7. If you look at the curve just now, at 90 mil, you have pH 2, 2 point something, which is 2.28. But at equivalence point, the pH value jump up to 4.72 pH unit to pH 7. Okay, so this is how much the pH has changed because the pH at equivalence point is 7. Okay. Now, let us continue for our titration curve. At 90 mil, the pH was 2.2. Here is pH 7. Okay. 2.28. Okay, so you continue plotting the titration curve at 100 mil of NaOH. Now, what happens if we continue adding titrant into our analyte past the equivalence point? The pH would become basic. Okay, and what we have is excess of hydroxide ion because we keep on adding NaOH into our analyte. Okay, so this is what we call also over titration. Over titration is when the titration continued past the equivalence point. Okay, so what happens if we have 10 mil over titration? So we have to calculate excess of hydroxide ion. So we have mole excess of hydroxide ion minus mole of hydroxide ion minus mole of H plus ion or hydronium ion divided by the total volume. Total volume here is the volume of analyte, which is 100 mil. It is always 100 mil plus volume of over titration. Okay, so at equivalence point, you already have 100 mil. So 100 mil plus 10 means you have 110. Okay. So that's why you have here 110 mil. This is the volume of NaOH added to your analyte. This is the volume of your analyte. And this is the total volume of NaOH plus the analyte. Okay. Okay, from there you can calculate the molarity of hydroxide ion. From the molarity of hydroxide ion or concentration of hydroxide ion, you get the POH equals to negative log OH. Okay, and from POH you can get the pH. pH equals to 14 minus POH. So these are the answers. Okay. If you look at the pH given here, you get 11.68, means you are on the right track because over titration always means that the pH would be basic and higher compared to 7. Okay, higher than 7. So this is true for any strong acid and strong base titration. Okay, but it is not necessarily true for a strong acid and weak base titration or a strong base and weak acid titration. This is Now, if you look at the titration curve, if you keep on calculating for every 10 mil additional titrant added to the analyte, you will have calculation for 110 mil of titrant up to 200 mil of titrant. You can go on, but it is not necessary. I This is good enough because you see that there is not much difference in the change of pH after the equivalence point. If you look at this value, 11.68, 11.96, 12.11, and 12.52, even after additional of 100 mil extra titrant to the analyte. So this is how the full titration curve looks like. If you look at the area or the curve before the equivalence point, this is it. Okay, from 0 to 90 milliliter of NaOH added. So if you see there is not much change in the pH, although it keep on increasing because you keep on adding titrant into the analyte. However, at the equivalence point, it jumped to pH 7. And after the equivalent point, um, the increase in pH is not very clear. Okay, it's not very significant. It's increasing, but in a small number. All right. So this is basically how you construct titration curve for any acid and base, strong acid and strong base titration. There are some important points that you have to take note, which is at equivalence point for strong acid and strong base titration, it is always pH 7. That's point number 1. Point number 2, before equivalence point, you have to calculate the excess hydronium ion. Okay, and you know that the pH is less than 7. And point number 3, post equivalence point, or we call it over titration, you know that the pH is always more than 7, and you have to calculate the excess of hydroxide ion. From there, you get POH, and then you recalculate it for pH. Okay, so that's about it for a strong acid and strong base titration. You're going to use the same approach to solve for any strong acid and strong base titration, whether it is sulfuric acid, phosphoric acid, hydrochloric acid, or any strong acid with any strong base such as sodium hydroxide, potassium hydroxide, or calcium hydroxide. So you know the list of strong acid and strong base. If you look at the questions, and the question is listing the type of acid which is strong base and strong acid, just use this approach for calculation. So this has been mentioned just now. From the start of the titration to the near of equivalence point, the pH goes up very slow. So these are the area, okay? But after the equivalence points, it also goes up very slow. The only part which you see the equivalence, which you see the pH increase rapidly, is at the equivalence point. Okay. So at the equivalence point, you know that moles of acid is equal to the moles of base, and the solution contains only water and salt from the cation of the base and anion of the acid. So the pH is always 7. Titration of a strong base with a strong acid. So if we plot pOH rather than pH, the results will still look identical. For example, just now we know that for any titration curve, we know that it's the plot of pH against the volume of titrant. Okay, but if we choose to use pOH rather than pH for plotting the titration curve, the results will still look identical. Typically, we still plot pH versus ml of titrant, so the curve is inverted. Okay. So let's take a look at titration curve. The blue line means you start with a basic sample and end with lower pH. And at the equivalence point, you can see the pH is 7. If you start with acidic sample, you start with low pH and you end with high pH. And the equivalence point is still pH 7. Okay, so it doesn't matter if you start with an acidic or a basic sample, you still have the similar curve, but it is in an inverted manner. All right. Okay. The concentration of titrant affects the shape of titration curve, meaning to say that as the concentration of acid decreases, we get a less distinct jump in the pH. So in this curve shown in the slide here, if you look at these three curve, let's say you have curve A, curve B, and curve C. Which one do you think has more concentration of acid? So if you look at the statement here, as the concentration of acid decreases, we get a less distinct jump in pH. Meaning to say that between A, B, and C, A have lower acid concentration, followed by B, and C has the most acid concentration. Why? Because you see that there is a distinct jump in the pH, more compared to B and A. Right? So what happens when the concentration of titrant is reduced? When the concentration of titrant is reduced, we also have a less distinct in pH jump. So let's say you have curve A, curve B, and curve C. Which one do you think has more concentration of titrant? Of course, that would be A. It has the most concentration or the highest concentration of titrant because you see that there is more jump in pH, distinct jump in pH during the titration process. Okay. Now, plot and show calculation involve for titration of 0.1 molar 50 ml NaOH with 0.1 molar HCl. So again, you can repeat the same calculation approach as has been mentioned just now. First, you have to calculate how much volume is needed to reach the equivalence point. You use MAVA equals to MBVB. This is the first step. Second step, you calculate the pH before equivalence point. Third step, you know that the pH at equivalence point is 7, so you plot it. And step 4, you calculate the pH after equivalence point. So for step number 2, you are calculating excess of hydronium ion. And for step number 4, you are calculating excess hydroxide ion. All right? Okay, now let's take a look at the second type of titration between acid and base. Now we have titration of weak acid and weak bases with strong titrant. When we deal about weak acid and weak base, we know that from what we have learned in learning unit 4 acid-base equilibria, we know that all weak acids, they have their own conjugate base, and all weak base have their own conjugate acid. So whenever we talk about titration between weak acid and weak base with a strong titrant, we must concern with the conjugate acid and base pairs and their equilibrium. All right? This is just a revision. Let's say you have a weak acid HA dissociates in water to form hydronium ion and its conjugate base. So this is an a dissociation reaction that we have seen commonly in learning unit 4, which is acid-base equilibria. Now, let's take your notebook. Take your notebook and please have two separate tables for weak acid titration with strong base and another table for weak base titration with strong acid. Okay, you have each table like this for number 2 and for number 3. Okay, because we are going to calculate differently using different formula for both of the type of titration. For example, if the sample is weak acid, this is number 2, type 2. If the sample is weak acid, then use Ka equals to concentration of hydronium ion times concentration of conjugate base divided by the concentration of weak acid. So from here, we know that still we go back to acid-base equilibria discussion. We have known that concentration of hydronium ion here is always the same with concentration of conjugate base. So from there, you can calculate the pH value. So the pH value would be negative log concentration of hydronium ion. All right. Okay. So if you start with a weak acid, so you need to calculate the Ka. You need to calculate the concentration of hydronium ion using Ka expression. So what if you have weak base? What if you start with weak base? You need to use Kb to calculate the hydroxide ion concentration. So Kb is equal to concentration of hydroxide ion times the concentration of weak base. Times the concentration of acid or the conjugate acid divided by the concentration of weak base. Okay. So here we know that the concentration of hydroxide ion is equal to the concentration of a conjugate base. So we can calculate the pH value by using 14 minus POH. Of course, from OH, you can get POH. Okay, so POH is equal to negative log OH. So from there, you can calculate the pH value. All right. Now, if you start with an acid, how do you calculate pH before equivalence point? You use the Henderson-Hasselbalch equation using pKa. Okay, and if you are calculating the titration, the pH before equivalence point, when you start with a weak base, you can use this formula. pH equal to 14 minus Henderson-Hasselbalch equation in the form of pKb. Okay, so just jot down this formula. So at equivalence point, what happened? At equivalence point, all sample is converted to its conjugate form. And if the sample was an acid, you solve the pH using Kb relationship. And if the sample was a base, you solve the pH using Ka relationship. If you look at your notes, you know that when you begin with an acid, you should calculate the initial pH using Ka expression. But at equivalence point, you should calculate the pH using Kb expression. If you start with a weak base sample, you calculate the initial pH by using Kb expression, but at equivalence point, you will use Ka expression. Why? Because when you start with a weak acid, you already know that the initial pH should be acidic pH. Okay, and when you start with base, you should know that the initial pH should start with basic pH. So you use Kb. However, when you use acid titrated with a strong base, at equivalence point, you need to calculate the pH using Kb expression because the pH of your analyte would be at basic pH. This is if you start with an acid, okay? And if you start with a weak base, the pH at equivalence point would be acidic. Okay, so it's the other way around. It's the opposite for both weak acid and weak base. Okay, so Kb plus Ka equal to 14. This is the thing you have learned in acid-base equilibria. So now let's take a look what happened over titration. Meaning to say that if you keep on adding your titrant to your analyte, okay, so for over titration, it's identical to a strong acid and strong base formula. We need to account for the amount of excess titrant and how much it has been diluted. Remember, for case number 2, titration of weak acid with strong base, you need to calculate excess hydroxide ion. For over titration, if you start with weak acid, you need to calculate the excess of hydroxide ion for over titration. But if you start with a weak base, or case number 3, you will have to calculate the excess of hydronium ion for over titration. Why? Because in case number 2, you are titrating it with a strong base. And in case number 3, you are titrating it with a strong acid. Okay, so you add more acid, you get more hydronium ion. You add more base, you get more hydroxide ion. Okay. So how do you calculate this? You go to the example for titration between strong acid and strong base to know that. If I may summarize it, excess of hydroxide ion is millimole of base minus millimole of acid divided by the total volume. Okay, so this would be MAVA. This would be, sorry, MBVB. This would be MAVA. So excess of hydronium ion would be millimole, excuse me, millimole of acid minus millimole of base divided by total volume. Okay. So this is for over titration. So what did you get for your notes now? You get a different formula for case number 2 and case number 3. Okay. So now we have learned 3 cases or 3 types of acid and base titration. Case 1, titration between strong acid and strong base. Case 2, titration between weak acid and strong base. And case number 3, titration between weak base and strong acid. So they will have different results. They will have different calculation. Okay. So you need to take note of all the formula for each of the cases. All right, let's take a look at this example. Let's say you have a titration between 100 ml solution of benzoic acid titrated with 0.1 molar of NaOH. So the question is asking you to construct a titration curve. First of all, if anytime you get any question on titration, you have to first identify which case is it. Is it case 1, titration between strong acid and strong base? Or case 2, titration between weak acid and strong base? Or case 3, titration between weak base and strong acid? So in this case, it is obviously known from the question that this is a strong base. NaOH is a strong base. And benzoic acid is a weak acid. So you need to use the formula for case number 2. Case number 2, which is titration between weak acid and strong base. Okay. So take a look at the formula you have. So again, the first step in any titration calculation is to determine how much volume needed to reach the equivalent point. So step 1, calculate the volume needed to reach the equivalent point. MAVA equals to MBVB. MAVA equals to MBVB. Okay. Don't get confused because of the strong acid or weak base or weak acid cases. In all cases of titration between acid and base, at equivalence point, they are always the same number of mole for acid and base. Okay, for any type of acid-base titration, at equivalence point, it means that the number of mole for both acid and base are the same. Okay, so you can use this formula for any cases of acid and base titration. So from this, you get the volume of titrant used to reach equivalent point is 100 ml. So anything below 100 ml should be considered points before equivalence point. Okay. So before titration, because you are starting with weak acid, which is the benzoic acid, you start with Ka. Ka expression, the purpose is for you to get concentration of hydronium ion. Okay. Now, this is how you calculate it. Ka equals to concentration of hydronium ion times concentration of conjugate base divided by the concentration of weak acid. So you assume that A conjugate base is negligible to compared to the acid. Okay, but you still know that it's X. Where do you get this X? You go back to LU4. You know that Ka equals to concentration of H plus ion or hydronium ion times concentration of conjugate base divided by the concentration of weak acid, Ha. Okay, so this and this is normally the same. So when H is X, conjugate base is also X. So you get from there X square. From the calculation, you get X. So from X, you can calculate pH. pH equal to X is actually the concentration of hydronium ion. Okay, so you can have pH equal to negative log concentration of hydronium ion equal to 2.6. So this is before titration. What happened after 10 ml of NaOH is added? So you need to calculate excess acid. Okay, excess hydronium ion. Why? Because you are starting with weak acid. You are starting with weak acid, so you know the pH is acidic. So you know that before reaching the equivalence point, you have to calculate the excess concentration of uh, acid. Okay. So concentration of acid is excess acid. Okay, excess means mole unreacted. It's the same thing. Okay, so you have number of mole of acid minus mole of base divided by the total volume. Okay, so you know that the concentration of benzoic acid is 0.1 molar. You know the concentration of benzoic acid is 100 ml. It's always 100 ml. And you know the concentration of NaOH is 0.1. This is from the question. And you know that the volume is 10 ml now because you just add 10 ml. But later on, if you add 20 ml, 30 ml, you have to change this to 20 ml, 30 ml. Okay. So the total volume is the combination between the analyte 100 ml and also the addition of NaOH 10 ml. So this become 110. So from there, you can calculate the concentration of excess hydronium ion. Okay. Right. So excess of hydronium ion and excess of conjugate base. So conjugate base here, which is the benzoid, is moles of NaOH added divided by the total volume. So you have MV here, 0.1 times 10 mil divided by 100 mil, you get 0.009 molar. So pH here is equal to Henderson-Hasselbalch equation. Remember, pH equal to pKa plus log K something something. Okay, so you go back to the Henderson-Hasselbalch equation. Okay, so from here you can get the pH. So how do you get the pH? For all the points before the equivalence point, you have to repeat all the steps in this slide. Step number 3. Okay, for all the volume, every 10 mil, 20, 30, 40 until 90 mil. Why? Because at 100 mil, you will reach the equivalence point. Okay. If you look at here, there is not much changes in the pH, but the pH is changing towards higher pH. Okay, so what happened for the titration curve? You can plot pH versus mil of titrant. So here you can get the curve which comes from the value here. Okay. Now what happened at equivalence point? So at equivalence point, when you have 100 ml of titrant, this is from our initial calculation just now. We know that we need 100 ml of titrant to reach the equivalence point. And remember, if you start with an acid sample, at equivalence point, you need to use Kb relationship to calculate the pH. Okay. So, if the question is given you Ka, if you look at the question just now, let's go back to the question. Okay. If you look at the question here, it's giving you Ka and pKa. So, how do you get Kb? You get Kb from the expression Kw equals to Ka plus Kb. Sorry, Kw equals to Ka Kb. Okay. So if you start with a weak acid, you should use Kb relationship at equivalence point. This is to calculate Kb. Kb equals to Kw divided by Ka. So you know Kw is always 1 times 10 to the power negative 14. Always and forever. Okay. Divided by Ka, which is given in the questions. So you get Kb of this value. So from Kb, you can calculate the pH at equivalence point. So at equivalence point, you know that the number of moles for benzoic acid is equal to the number of moles of NaOH because they are at equivalence points, meaning they are stoichiometrically equivalent. Okay, so the number of moles for benzoic acid and NaOH is always the same. Okay, for equivalence point only. Okay. And the predominating ion in the solution is the benzoate, which is the weak base or the conjugate base coming from the benzoic acid. So you know that at equivalence point, the concentration of benzoate is mole of acid divided by the total volume. So mole of acid is MaVa. So this is Ma. This is Va. Okay, and divided by total volume, which is 200. 200 comes from 100 ml of analyte. What is your analyte? Your analyte is the benzoic acid and plus 100 ml of NaOH, which is the titrant. How do we know we have 100 ml? Because we have calculated at the beginning of the solving the question that we need 100 ml of NaOH to reach equivalence point. So the total volume at equivalent point should be the total volume of analyte 100 ml and the volume of NaOH 100 ml. So total 200. Okay, from this we can calculate the molarity of conjugate base. We have diluted the sample and the total volume at this point is 200 ml, and we can assume that the concentration of benzoic acid is negligible compared to benzoate. Why? Because we know that we have already increased the pH after we add more NaOH into the analyte. Okay. So at equivalence point, again, we have calculated Kb. So Kb just now is 1.58 times 10 to the power negative 10. So it is equal to x squared divided by the concentration of conjugate base at equivalence point, which is 0.05 molar. So this is taken from the concentration of conjugate base. So from here, you calculate what is X, and from X is concentration of hydroxide ion, and from concentration of hydroxide ion, you can calculate POH. POH equal to negative log concentration of hydroxide ion, and you get 5.55, and you calculate the pH 14 minus the POH. You get 8.45. So you repeat this calculation for every 10 mil additional NaOH. Okay. For over titration. Okay. Right. So for over titration, you calculate the excess hydroxide ion. Remember just now, the calculation for over titration is similar to the calculation for a titration between strong acid and strong base. Okay. For calculation of over titration. Okay. Alright. So from there, you have to calculate the excess hydroxide ion. Why? Because you start with a weak acid. So at equivalence point, it becomes basic, and after equivalence point it becomes more basic. Okay, so the pH will increase, so that's why you are calculating excess of hydroxide ion. So from there you can have the pH. So putting it into the table for every 10 additional NaOH for over titration, and then you construct the titration curve. So this is area before the equivalence point. This is the equivalence point, and this is past the equivalence point, which is the over titration. Now, if you look at the exercise given here, the example given here, you can use the same approach as we have discussed just now. The question is asking you to calculate and show the titration curve for titration between acetic acid and KOH, which is potassium hydroxide. So we know from the question that this is a titration between a weak acid, which is the acetic acid, and a strong base, which is the KOH. So this is case number 2, titration of a strong a weak acid with a strong base. So you use the step of calculation that we have discussed just now.